Imagine starting with pure static, like a blank TV screen. This is a good analogy because, like TV static, the input image at the final forward step is completely random and contains no recognizable information. However, unlike real TV static, which might have some underlying structure from broadcasting noise, the noise we had here is perfectly Gaussian and truly structureless. What if you could teach a computer to slowly, step by step, remove that static until a perfect image emerged?
That sounds like magic. So we're not telling it what to draw, just how to clean up a mess?
That cleaning up a mess intuition is accurate in that the model removes unwanted elements. But unlike cleaning a physical mess, where you might have to decide what to keep, here the mess, noise, is specifically engineered and known, so the model learns a very precise removal process.
And the result is high-quality image synthesis?
Precisely. This paper, Denoising Diffusion Probabilistic Models, or DDPMs, introduced a groundbreaking approach to do just that in 2020. They built upon earlier ideas, but this work provided critical insights and simplifications, particularly the reparametrization of the mean and the use of the noise prediction objective, which made diffusion models practical and effective for generating images.
It says they're latent variable models. We've talked about those with VAEs. Does that mean there's some hidden compressed representation involved here too?
It does in a sense. The latent variable here relates to the noise level at each step. We're effectively tracking the image's journey through different states of noisiness. The authors state directly, we present high-quality image synthesis results using diffusion probabilistic models. This was significant because many previous generative models struggled to produce visually coherent and high-resolution images reliably without artifacts. DDPMs offered a new path to achieving this visual fidelity.
That's a strong claim. So before this, what were the main challenges in getting really good, diverse images from generative models?
Generative adversarial networks, or GANs, were dominant, but they often struggled with mode collapse and training stability. DDPMs offered a new path. These metrics, like inception score and FID, tell us how realistic and diverse the generated images are. These numbers were impressive for their time. They even claimed sample quality similar to progressive GAN, a leading GAN architecture then. This showed diffusion models could compete with the best, but with a different mechanism.
So it was a whole new way to think about image generation that matched existing state-of-the-art? That's definitely intriguing.
Exactly. The core insight is that by meticulously reversing a simple noise process, we can generate complex data. Let's see how that fixed process works.
All right, so how do we go from an actual image to pure noise? And why is that useful?
Think of it like this. You have a clear photograph, and you keep adding a tiny bit of static to it, over and over, until it's just pure static. This is similar to how a photo might degrade over time or with a poor signal, losing its original features. The key difference here is that we meticulously control how much static, Gaussian noise, is added at each step, making the process perfectly reversible in theory. The diffusion model's job is to learn the exact reverse process, how to remove that static step by step to get back to the original image. The article explains this with two processes. First, a fixed forward diffusion process of our choosing that gradually adds Gaussian noise to an image.
So the forward process is like a known recipe for messing up an image? We control exactly how much noise is added at each step?
Yes, it's a predefined corruption. Each step adds a bit more noise, and crucially, it's always Gaussian noise. Eventually, you end up with pure noise. It's like repeatedly shaking a clear glass of water with a tiny bit of dirt until it's completely murky. This captures the gradual, irreversible mixing. The analogy is good for understanding the progression to total corruption. However, in our model, the dirt is specifically Gaussian noise, which has mathematical properties that allow for a controlled, learnable reverse, unlike physical dirt particles that might be impossible to fully separate. The second part is the learned reverse denoising diffusion process. This is where the neural network comes in, trained to undo that fixed forward process.
So the network observes how the noise was added and tries to learn how to subtract it? That makes sense intuitively for generating an image.
Let's take an image of a cat. In the forward process, we add a little noise, then more, until it's just static. The reverse process starts with that pure static, and the network predicts what to remove to get a slightly clearer image, then repeats until a cat appears.
The article mentions sampling from a conditional Gaussian distribution at each step. Does conditional mean the noise added depends on the current image?
Exactly. The amount and type of noise added in the forward pass depend on the image at the previous time step. It's not just random noise added globally. Crucially, the article says we don't know the true reverse distribution directly. It's intractable, as it would require knowing the distribution of all possible images.
Ah, so this is why we need the neural network. It's approximating that unknown reverse process rather than calculating it directly.
Yes, we leverage a neural network to approximate, learn, this conditional probability distribution. Specifically, the neural network learns to predict the mean of this conditional Gaussian distribution at each reverse step. While the variance is often kept fixed in the basic DDPM, predicting the mean is the critical mechanism for guiding the denoising.
And this approximation is what allows the model to become effective and adaptable by learning directly from data to capture complex image distributions rather than relying on hand-engineered rules.
Right. Now let's dive into how this neural network learns. What is it actually trying to predict to achieve this denoising miracle?
Okay, so we have a forward process that adds noise. What's the network's specific objective in the reverse process?
Instead of directly predicting the denoised image, the DDPM authors found it was more stable and effective to have the neural network predict the added noise.
Wait, so it's not predicting the image, but the noise. That's a subtle but important difference. Why predict the noise itself?
Think of it like this. If you know exactly what noise was added, you can simply subtract it to get the cleaner image. This is precise in the mathematical sense of vector subtraction. What makes it different from simply removing a filter is that the noise isn't just a simple layer. It's intricately mixed with the image data, so the model needs to intelligently discern and remove it. The network becomes a noise predictor. This reparameterization simplifies the learning problem significantly because the noise is a clean Gaussian, while images are complex. This leads to an elegant objective function, simple mean-squared error, MSE, between the true and the predicted Gaussian noise. This MSE directly optimizes the neural network to output the correct noise, which in turn allows us to compute the denoised image for the next step of the reverse process. It's a direct way to teach the network the precise subtraction needed.
So the network predicts a noise pattern, and we compare it to the actual noise we added in the forward step. That's very direct.
During training, we take a real image, sample a random noise level, and corrupt the input by this noise at level T. Then, the network sees this noisy image and tries to output exactly the noise that was added. We minimize the difference. For the neural network architecture itself, DDPMs typically use a unit. We've seen units in hashtag TCM 093004 with transformers, but their structure is well suited here.
Ah, the unit that downsamples then upsamples with skip connections. So it's basically an autoencoder, but for predicting noise at various scales. It's basically an autoencoder in its encoder-decoder structure. However, it's crucial to remember it doesn't aim to reconstruct the original image, but specifically to predict the noise components.
Exactly. The UNet has a bottleneck in the middle that makes sure the network learns only the most important information. This helps it capture features at different resolutions, crucial for understanding both fine details and overall image structure.
And those residual connections between the encoder and decoder are key. They allow information from earlier layers to directly reach later layers.
So it's not just about compressing and decompressing, but retaining detail through those shortcuts, ensuring gradients flow well during training.
A common confusion is thinking the unit outputs the clean image. Instead, it takes in a noised image at a particular time step and returns the predicted noise. The clean image is then derived by subtracting this predicted noise from the noisy input. This is a very robust way to train.
So, DDPMs are powerful, but they operate directly on pixels. This can get expensive fast. What if we could do all this in a smaller space?
Generating high-resolution images, pixel by pixel, sounds incredibly compute-heavy. There has to be a more efficient way. This paper highlights a critical issue. Diffusion models typically operate directly in pixel space. What's the problem with that for practical use?
It means every step of the denoising process involves huge tensors if your images are high resolution. Training becomes slow and computationally expensive.
Exactly. The authors explicitly state that the optimization of powerful DMs often consumes hundreds of GPU days, and inference is expensive due to these high-dimensional operations.
So the core mechanism works, but scaling it up for truly high-resolution images hits a wall because of the raw data size.
That's where latent diffusion models, or LDMs, come in. Instead of operating on raw pixels, they apply the diffusion process in a lower dimensional latent space.
Ah, like a secret compressed world where the denoising happens much faster because there's less data to process at each step?
Precisely. The first step in an LDM is to learn an efficient and perceptually equivalent representation space using an autoencoder. This autoencoder compresses the image data.
So before any diffusion, an autoencoder takes the high-resolution image and turns it into a smaller but still meaningful representation?
Yes, this autoencoder that maps images into a lower dimensional latent space is crucial. It acts like a smart compressor, retaining all the important visual information while discarding redundant details. Once an image is encoded into this compact latent space, the DDPM's forward and reverse processes, adding and removing noise, are applied directly within that smaller, more efficient representation.
So the diffusion model isn't seeing pixels of a dog, but rather a compressed dogness vector, and it's denoising that vector. And then the autoencoder's decoder turns the final denoised latent back into a high-res image.
Exactly. The diffusion model learns to synthesize representations in this latent space. After the latent is denoised, the autoencoder's decoder reconstructs the final high-resolution image from that clean latent representation. This two-stage process allows us to scale up. This approach allows them to significantly reduce the computational cost of training and inference while maintaining or even improving the generation quality. It's a game changer for practical applications.
So we get all the benefits of high-quality diffusion generation without the astronomical GPU costs. That makes it accessible for so many more researchers and artists.
Beyond efficiency, LDMs are incredibly versatile, enabling various conditional image synthesis tasks, including text-to-image synthesis.
Wait, so this is how models like Stable Diffusion work? You type in a cat riding a skateboard and it generates it by guiding the denoising and the latent space?
Precisely. The conditioning information, like text, is used to influence the noise prediction network within the latent space, steering the generation towards the desired output. In essence, LDMs are efficient, flexible, and achieve state-of-the-art performance while significantly reducing computational requirements.
From theoretical static removal to generating complex scenes from text, it's amazing how this core idea evolved into something so powerful and widely used today.